All right, when your physics teacher is also your math teacher, you get to do extra mathy stuff in physics. I know you're all pumped about that. But what we're going to do is derive the kinematic equations. Derive just means we're going to start with what we know and we're going to work towards what we want. So when we're looking at this one, the final velocity equals the initial velocity plus the acceleration times the time. We're going to start with what we know. And what do we know? We know that acceleration equals the change in velocity over the change in time. Well, we also usually write this as our final velocity minus our initial velocity over the change in time here. So hopefully it's pretty obvious where we're going from here. I have to multiply both sides by time to get time out of the denominator. So time divided by time is just 1. So that leaves this alone over here, and I have acceleration times time equals the final velocity minus the initial velocity. Well, I'm solving for final velocity, so I'm just going to add initial velocity to both sides. When these cancel out because they equal 0, I get that the initial velocity plus the acceleration times the time equals my final velocity, which is the equation. Start with what we know about acceleration here. We can just morph it around and get to this equation. This one is by far the easiest to derive because it's basically just telling us the definition of the average. It says the average velocity is 1/2 the initial velocity plus the final velocity. So if you remember, whenever you're taking the average of something or the mean of something, you sum the parts and then divide by however many there are. So we have initial velocity, we have final velocity, and then since that's two things, we divide it by 2, and that gives us our average velocity. Not too much deriving there. This one's pretty obvious too. We actually used it last unit because we know that the velocity is some change in position over some change in time. So when we multiply both sides by time, time by time is 1, and my change in position is going to be my average velocity times my time. Here's where we get to have a little fun. Where does this come from? Well, I see a change in position here. Let's use this. I know that the change in position is my average velocity times my time. But I also know that my average velocity is the final velocity minus or plus the initial velocity divided by 2 times time. All right, here comes the fun because we know that the final velocity is the initial velocity plus the acceleration times the time. So since we know that, we can take this and plug it in for my final velocity. Why do we want to do that? You'll see in a second. So all I've done is taken what we already know. This is one of our equations. I plugged this in because it equals the final velocity. So I put that in place for the final velocity here. All right, well now I've got initial velocity plus initial velocity, and that's 2 initial velocities, plus acceleration times time, all divided by 2, all times time. Okay, well, we can divide each one of these guys. 2 initial velocity divided by 2 is just straight up initial velocity. And then, or acceleration times time divided by 2, that is 1/2 acceleration times time. And you see where we're going. All right, and we have to times this whole thing by t, so we're just going to distribute that. T times initial velocity is initial velocity times t, and t times 1/2 at is 1/2 a, and now t squared, because there's 2 t's. And that all equals your change in x. Hey, that's the equation we were looking for. All right, one more. This one is by far the most complicated. I will walk you through it. I'm not going to expect you to know all the algebra, so don't freak out about it. Just follow along the best you can. So, we're going to use some things that we know. We know that final velocity is initial velocity plus acceleration times time. And the goal with this one, the good thing about this equation is you don't need to know the time. It's the time independent equation, independent of time. So what we're going to do is solve this guy for t so that we can plug it into another equation that we know, and then solve it so that t no longer exists in the equation. So to solve this for t, I first have to get rid of initial velocity on this side. That's now 0. We have the final velocity minus the initial velocity is now a times t. Well, I'm solving for t, so now I need to divide both sides by a. A divided by a is 1, and 1 times t is t. So we get that the final velocity minus the initial velocity divided by the acceleration is the time. I promised you we'd use another one that we know, and we just figured this one out. We know that the change in position is our initial velocity times the time plus 1/2 the acceleration times the time squared. Okay, we don't want time in here anymore. So we solve this guy for time so that we could plug him in. So he's now going to go in for all the times, and then we'll be rid of times. All right, let's look at what that looks like. Okay, so I've just taken this and put it in for t. Instead of writing t, I wrote this, because that's what t equals. Substituted it in. Okay, we're going to do a lot of math right here. We're about to go algebra crazy on this, so this is what I'm not expecting you to have to follow through with. This is algebra 2 kind of simplifying, so just follow along as best you can as I do it, and here we go. So, first things first is I'm going to simplify this side. Well, that's what we're going to do the whole time. I'm going to multiply initial velocity into here. I have to distribute, though. So, we get v sub naught, v final, minus v sub naught squared over a plus 1/2 a. I have to square this, 1/2 a. And then this is a binomial. If you don't know what that means, don't worry about it. We're not going to do the math. Minus 2v final, v initial, plus v sub naught squared, all over a squared. Now I need to multiply this in. So once I've squared this, order of operations says I need to multiply this in. So 1/2, that 2 is going to go on the bottom down there. So we got 2a. We're also multiplying by a, so that's going to cancel out one of these a's down here. So that's done. So I've got v final squared. And we're adding that to v initial, v final minus. Okay, so now I need a common denominator since I'm adding fractions. So what I'm going to do is multiply this guy by 2 over 2. 2 over 2. And that's going to get me to 2a. 2a is obviously the common denominator, so I'll have, I have to distribute this 2 up here. 2v sub naught v final minus 2v initial squared all over 2a plus this thing. Okay, now that I have a common denominator, I can add them and put them all over the same denominator. I'll put the like terms together right now. So I've got a v initial v final here, and I've got a v initial v final term here. This is a positive 2 and a negative 2, so those are going to go away. Those cancel each other. I've got a v final squared and no other v final squared, so I'm going to leave the v final squared. I've got v initial squared here and v initial squared here. Those are like terms. So I've got a plus, that should say plus. This is a plus v squared, v sub naught. So I've got 1 positive and 2 negatives. That leaves me with 1 negative. So I've been simplifying this side, and of course on the left side it equals change in x. So if it equals change in x, and the original equation is in terms of v final squared, I'm going to solve for v final squared. So I'm going to multiply both sides by 2a. 2a divided by 2a is 1. Now I have 2a times change in x equals v final squared minus v initial squared. I can add v initial squared to both sides. That's now 0. And v final squared equals v initial squared plus 2 times the acceleration times the change in your position, which is our final equation. Hooray! All right.